doesn't need any introduction.
Okay, well, this I think doesn't work. Was working before. So this is a nice experience for us because then we can check that everything is fixed. And all the things that we have to fix when we will be organizers for the next sessions. Today I'm going to present a work that I have done in collaboration with some other researchers, Josu Lim, who is in the audience, I guess. Yes, there. She's postdoc here in this institute, also with Rob Thicko, who was here for visiting us for 1 month, Jean Martinec also, and Pascal Simon. So the topic that I'm going to present this work is related with the Kondo effect. Is the main topic in which I'm doing, well, one of the main topics in which I'm doing my research work, and it was the topic of my PhD thesis. So then I'm kind of expert on Kondo physics. So I will try to introduce you or motivate you why this is an important effect in quantum transport. So then the outline is first. Thank you. The first is to talk about the Kondo effect in nanostructures. So I will try to motivate, as I said, why Kondo effect is important. And then I will introduce you why we study two Kondo impurities, not only one but two. And finally, I will end up with a recent work on ferromagnetic contacts. And I will explain you why. I will explain you the role of the ferromagnetic contacts in the Kondo effect and how we model ferromagnetic contacts. Okay, so usually we talk about the spin Kondo effect in many different systems, in lateral, vertical, quantum dot. We also very recently have discovered that not only Kondo effect in the spin sector can appear, but also in the orbital sector, in carbon nanotube, in fullerenes, in many graphene-based nanostructures. We have also seen experiments in quantum wires with huge anisotropic G factors, with huge Thiemann splittings, in squids with superconductors, interferometers with two dots that makes an interference pattern between the transport between both dots, etc. And the contacts can be normal, superconducting, ferromagnetic. Also, we can attach, instead of big reservoirs of electrons, we can attach some metallic grains that they have some current interaction inside as contacts. With this list here, I was just to tell you that Kondo effect is now studied in many different systems. So before it was just a study in metals with magnetic impurities, but now there is plenty of systems in which you can study Kondo effect, and these systems are handmade. So the new thing in Kondo effect appears in 1998 when the first experiments were done in quantum dots. And the basis species of Kondo effect is the following. We can understand this with just a simple molecule like this, okay, with some hybridization that allow you to have electrons jumping from one dot to the other. So we have this tunneling between two sides, okay, and we have also the Coulomb interaction in the way that you have to pay some energy if you want to put two electrons in one side. Okay, if you have two electrons here, then you have to pay some energy. Okay. So the combination of U and T is the interdot tunneling, make that at the end the ground state for large values of U, okay, when U is large enough, then this makes that at the end the ground state is an antiferromagnetic, is a singlet state, which means that both interactions, the Coulomb interaction and the kinetic energy due to the interdot tunneling, okay, at the end, the work of both interactions in common just results into an effective antiferromagnetic interaction between the spin of the dots. So at the end, the spin of the sides, the two spins here sitting in each impurity, they want to form a singlet state. So this is the main message, and you can see how this is built. In this way, you can start with a configuration like this. This is for the first side. I feel that I know what happened. Now I have to put some caffeine. Now it
doesn't get sleep.
So then, if you calculate at second order in the tunneling Hamiltonian, okay, you can build a tunneling term that connect this side to this. If you make a perturbation theory in the tunneling Hamiltonian for this type of processes, you have some virtual state in which you have to pay some energy that is U, okay? And then at the end you end up with a situation in which the spins has flipped, okay? You have a second order processes in the tunneling with an intermediate virtual state that pays some extra energy U. It's a virtual state because you don't have this energy actually, but due to the Heisenberg principle, you can allow this type of virtual processes. So you end up with a system that the two spins have reverse. So the energy that you gain is proportional to minus t squared over u, and you can mathematically write this type of processes in this way, in a way that the spin of one of the impurity or the side one has lower, and the spin in the second side has increased, and the opposite. Okay. So at the end, what the system prefers is to build a singlet state between the two spins of the two sides, okay, and the effective interaction is antiferromagnetic.
So there is no magnetic interaction between the spins, which is what you mean?
There is no magnetic. It's something that is caffeine is
the Coulomb and this exchange interaction that turns out to
is generated by both.
Yeah, I think the antiferromagnetic is more metaphoric in the sense of how the spins are aligned, but really magnetic interaction.
Well, at the end, it's a magnetic interaction that is built because of the work of the Coulomb interaction and the interdot tunneling or interside. You build. I mean, you can just write a Hamiltonian for the two sides. You can make a transformation, kind of a canonical transformation, and you end up with some type of Heisenberg Hamiltonian, J S1 S2. So,
yeah.
Yes, it's clear.
And the energy gain that you wrote is for which process?
Yes, you gain this energy whenever the spins are free.
But the system doesn't have the same energy if it is up and down and up? Or
Yes, you just flip and then you gain this energy. Yes.
But I don't understand. If you start with up and down and you flip, you gain energy, and you recover this and you gain energy again.
No, you flip, and in this way you gain the energy. So they are flipping all the time, and you build this. They want to be anti-aligned.
Yeah, but if you start with an anti-aligned configuration and you flip, you gain energy.
So initial final state.
And then you flip both again, and you gain energy again.
No. I think
No, they are not eigen states of the Hamiltonian. The refused Hamiltonian that she
Yes.
before, the eigen state is a singlet. So a singlet is down up minus down up down.
Yes.
So depending on whether you start from one
You end with the
system,
other.
one state, one kernel of a system or not, then, I mean, that's why, I mean, she said that.
But what probably you say is that the gain of energy is with respect to the situation in which there is no tunneling. I mean, if you include the tunneling,
Then
you obtain a gain state which is the
you
simple one,
the
where you have a lower energy.
by
And
having
in
this
which
type
there's
of
correlation between
processes.
the spins in the sense that they are anti-aligned.
Yes. They prefer to be anti-aligned.
Anti-aligned but coherent.
Coherent.
Because you can have that also the state in which is anti-aligned but without a combination between them, and this has higher energy.
So now this situation can be extended to a more involved situation in which you replace one of these impurity by a continuum. So then this is kind of metal. If you think about electrons here, and you have a localized spin that interacts with the continuum by some tunneling. Okay. So then the Kondo physics arise in this type of systems when you have some continuum state that has some localized spins, some magnetic moments inside. So now the Hamiltonian that you can write is a type of Anderson Hamiltonian where you have the continuum here, where K is the wave vector that labels the electrons in the reservoir. Okay, you have the level of the localized impurity, the energy that you have to pay if you add 2 electrons in the localized side here, so you have to pay always U, and the tunneling between the two systems. Okay. So now, by doing the same type of perturbation theory, you can write a kind of effective Hamiltonian in a way that you have some coupling constant that depends on this B, small b, is actually this capital B, which means that this is the tunneling, and you have some denominator that depends on U, on the on-site interaction. And then you have, as before, some type of process that lowers the spin of the impurity or rise the spin of the impurity, and at the same time change the spin density in the continuum. The processes are similar to the previous one in the sense that you have the F electron that describe the spins in the impurity, okay, and the electrons that are in the continuum. And you can make this type of second order perturbative process in a way that you flip the spin of the impurity, okay, through a state that is empty, or through a state that is doubly occupied here. Okay, these two type of process are actually these two terms here. Okay, so this just has the information about process that flip the impurity spin through an empty state, and these are processes that flip the impurity spin through a doubly occupied state. But at the end, what matters is that you have some type of magnetic interaction that is antiferromagnetic. The important thing is that you form a singlet state between the localized spin and the continuous electrons, the continuous states here. I mean, you have a singlet state between the localized electrons and localized spin here. And at the end, what the impurity is doing all the time is just flipping. Okay, so the screen of the impurity at the beginning was with some magnetic moment, finite magnetic moment, but at the end, due to this spinning effect of the spin of the impurity, is just zero. I mean, it's totally spinning. Okay? So then the system prefers to flip all the time the spin of the impurity and form what is called many-body state, that is a singlet state. And it's many-body because electrons that are in the reservoir are participating in the formation of this singlet state. This is the main ingredient to understand the Kondo effect. It's a many-body state, yes.
So in the effective Hamiltonian, the S minus is for the localized spin.
Yes, and you can build.
The other ones are
Yes.
momentum.
You can build also some spin density.
And this K and the Q are the different momentum.
Yes, they
so
are
you have to
different
sum
momentum.
over all the momentum.
Yes, you have to sum. Okay, so now I have just explained the kind of origin of the Kondo effect, and we want to see this type of effect in quantum dots. Why quantum dots? Because you can imagine your localized spin as an electron in a quantum dot. A quantum dot is a kind of quantum well, okay, but the electrons are confinement in the three spatial directions. So it's like an atom. Here your energies are just discrete energies, and these two bars here, represented by gamma L and gamma R, are the tunneling barriers, and here you have some electrodes that are the contacts. So here you localize your spin, and you have coupling by tunneling with some continuum, okay, here, that are formed by the electrons in the reservoirs. So then you can talk about the left contact, the right contact, and the quantum dot. So the quantum dot is formed by discrete energy levels. You have to pay energy if you put two electrons in the quantum dot, so you have Coulomb interactions. They are in a way similar to atoms, but they are in a more tunable setup, because in an experiment you can tune this the transparency of the barrier, you can tune the width of the quantum dot, and you can gauge the level of the dot, which means to gauge the level of the dot means that you can put the level down or up as you wish. Okay, you can move the level of the dot, and the reservoirs are the contact, and you can apply some bias voltage. Okay, so you can allow to have transport from the left to the right. So the problem here is to calculate the current from the left to the right when many body effects are present, when Kondo effect is present. Okay. So here you see that if you put an electron in the dot, okay, you have to pay some energy, which is U, which means that your effective level has moved to here, okay? Some extra energy that is U. So, as I said, the most important thing is that now we can try to prove some non-equilibrium physics in the presence of many body effect. We can apply some voltage to the contacts, and we can measure the DIDV, what is called the DIDV, which is the nonlinear conductance, which is how the current changes as long as you change the voltage difference between the two contacts. And this can be proved that this is a measurement of the density of the states of the dot, which means that, sorry for this, this is, you can mimic how is the density of a state of this level by measuring the DIDV. So first, before entering in the Kondo effect, how is the linear conductance versus the gate voltage in a quantum dot before having a Kondo effect? Before you have what is called Coulomb blockade effect, and as I have already anticipated what is this. Coulomb blockade effect is just a situation in which you try to put two electrons in the quantum dot, but you don't have sufficiently energy. Okay? So if this electron is here, and you try to put another electron like this, then the level is renormalized because of U, okay, and then you cannot you don't have this, you don't have actually this energy to put one electron at such a high energy level, okay? You don't have this energy. So then what you can do, you can just gate this level, you can put this level down here, okay? And then the next electron, okay, can enter in the dot, okay? At the energy that is given by the energy of this level plus U, okay? And then they can be transported. They can just go out, okay? This will give you two different peaks in the linear conductance. The linear conductance is more or less the current, but when the bias voltage is very small, okay? So then you can see that you have two peaks. One peak is when this level is aligned with the Fermi energy and there is no electron in there. So if there is no electron, then you can put one electron there and just jump to the right contact. So then you get one peak. And the other peak is when you have already one electron in the contact, okay? If you have one electron in the contact, if you have one electron in the dot but is sufficiently low in energy here, then the next electron can enter and can go out. So then you have the other peak. So this means that if you move this level, as long as you move this level, you have one peak that gives you the transition from 0 to 1 electron, and the other peak that gives you the transition from 1 to 2 electrons to the dot. And there is a region in which the transport is completely blocked because you don't have sufficiently energy to put 2 electrons in the dot. So what happens when you have Kondo effect? When you have Kondo effect, now the nice thing is that if you repeat the same measurement but in the presence of Kondo effect, then you see that you get this curve, and now where before the transport was blockaded completely, now the transport is perfect. It's just unitary. Okay, you get the maximum of the conductance, that is 2e squared over h. And this is because of the Kondo effect. This is something, well, I think is really amazing, because before you could only have two situations to have transport, either here or here. But now you have just a complete window of values of the gate, which is epsilon naught, okay, is the level of the dot, in which you have perfect transmission. And why is this? So before we have this situation in which you don't have the sufficiently energy to transport electrons, but now you can have transport. And why is this? This is because you form this singlet state, this many-body state. And the signature of this many-body state is a peak at the Fermi energy, okay, that remains there even if you change the gate of the dot, even if you move the level of the dot, the peak remains there. And this is the signature of having this many-body state. So
peak in what? In the conductance through the dot, or in what?
Sorry?
A peak in what? In the
density of the states. In the density of the states, you have always a peak here. Before you have only two peaks, one here and the other one here, that are the Coulomb blockade peaks. Okay? But now, because you lower the temperature, you need to lower the temperature for having for favor this situation, Kondo effect. You need to lower the temperature and then Kondo effect arises. And then you see how emerge a peak just at the Fermi energy, and then the transport is completely coherent and perfect all the time, whenever you have Kondo.
So then you basically have to form this coherent state between the dot and the continuum outside the dot. And normally, I mean, you have quite quick dephasing outside of the dot.
Yes, this is something that Kondo effect, if you have some source of dephasing, then this will quench this, of course. Yes. But usually you try to avoid sources of the decomposition of dephasing. Yes. You try to avoid this. And this now I think this is it's a common thing. Experimentalists can see this very frequently in nanostructures, with this type of pieces. So this is your impurity, this is your quantum dot, and the peak spin is just forming this singlet state, and the signature of this peak spin is like a peak at the Fermi energy. Okay, and the Bible of the Kondo effect is this book by Hison. Okay, so the linear conductance is maximum. You get the maximum value, and you get this for a broad range of parameters for the dot level. Whenever the dot occupation is odd, of course, as I said before, you need a localized spin. Okay, and a localized spin is always when the dot occupation is odd. You need an odd number of electrons because the electrons in the dot are filled up, down, up, down, up, down, and down, and up, for instance. Okay. So the up is forming this Kondo effect. And the finite density of states makes the dot perfectly conducting because the transmission through the dot is proportional to the density of states at the Fermi energy. So the conductance is proportional to the transmission, and the transmission is proportional to the density of states. And whenever you have a peak at the density of a state at the Fermi energy, you have maximum conductance. So this has been observed in experiments, and this is what is called the zero bias anomaly, or the DIDB, which is the density of a state at the end of the dot. And you see that this is the DIDB, this is the kind of density of a state of the quantum dot versus the drain source bias voltage, and you see a peak, okay, very high peak. Well, here is not very high because this experiment was done in 1998, but here you see that this peak can reach the unitary value, and you can see this in this linear conductance versus the gate because you see how the conductance gets the maximum value. This means that this piece just goes to the unitary value, that is 2 square over h. Okay. So, and this happens when you lower the temperature, this valley starts to grow, and then gets the maximum value. And this happens only when the dot occupation is off. Yes, please.
Do you know what the first two resonances are?
These are the Coulomb blockade peaks. The Coulomb blockade peaks, and whenever you fill the dot with 2 peaks, with an odd number of electrons, then you lower the temperature. And
so the first, but shouldn't you get a bridge between the two Coulomb blockade peaks?
Sorry?
Between the two Coulomb blockade peaks, shouldn't you basically get this bridge due to the Kondo effect?
Yes.
So then the first two peaks are
well,
different spin orientations of one electron?
Yes, but this also depends on the transparencies of the barriers, so you need to have some conditions. Okay, so maybe for these gate values, the transparency of the barriers are not large enough to make this Kondo effect. And only for these peaks here you have this. Okay. But the nice thing is you always have Kondo effect for odd number of electrons.
Yeah.
So the experiments were done in the labs of Goldhaber Gordon. At that time he was in the Weizmann Institute, Charlie Marcus in Yale, and Leo Cowell.
What are the different colors of the curves?
Different temperatures. So when you increase the temperature, then you see how this get the unitary value. Okay, numerical techniques to do this numerical randomization group. We have an expert in the audience, who is Johnson Lim, on this. So if someone wants to know more about this, can ask him. But it's only valid at non-equilibrium, and then there are other techniques that are important for treating many body problems, like diagrammatic techniques, green functions, using the slave boson representation, where these are very detailed things. Okay, but the techniques to attack a problem in which Kondo effect is present are kind of sophisticated techniques. Okay, and the equation of motion, and these are valid for treating non-equilibrium situations. the worst thing in the non-equilibrium situation is that the techniques are not so well developed that the numerical normalization group that is kind of exact approximation, but in systems. So more summary of what I said, the dot level position is normalized at the Fermi energy, which means that you always have this peak at the Fermi energy. The width of this peak is the Kondo temperature. So this means that if you increase the temperature, you kill the Kondo effect. The Kondo temperature depends on the dot parameters. This means that if the barriers or the level of the dot are not suitable for having a large Kondo temperature, you cannot observe Kondo effect. TK, which is the Kondo temperature, can be tunable in an experiment, and the DIDB is similar to the density of states, and at very low temperature, this peak is always normalized at zero, which means that the level of the dot is normalized at the Fermi energy, that usually is put at zero. Well, this is just a summary. Now, what happens when you have two impurities? Okay, when you have two impurities, now you have to assume that you have two Kondo clouds. Okay, one Kondo cloud is done in the left part. This dot is making its own Kondo effect with the left reservoir, and the right one is doing the same. But now the two dots, they touch each other because of T, the interdot tunneling. This is the well-known Kondo, the well-known problem of the two-impurity Kondo problem. Okay, and this has been observed again in metals with magnetic impurities, but has been more or less recently experimentally proved in double quantum dots. And this is the system that I have studied in many different situations. So you can have different regimes. One is this regime in which you can think about having each quantum dot forming its own Kondo effect. Okay, so you have two Kondo clouds, and if the barrier in the middle is sufficiently transparent, then the two Kondo clouds, they can talk each other, and you can hybridize both. So you can have a coherent channel between left and right through the hybridization of the two Kondo clouds. Okay, and this is the so-called bonding and anti-bonding Kondo states. It's the usual physics of molecular physics. So you have two sides, and then you can hybridize the two states of the two sides. And this is what I said. So for when the interdot tunneling is sufficiently high compared to the tunneling between each impurity and the cloud, okay, and the electrons here, when this T is larger than gamma, then you can hybridize the two Kondo clouds. And this has been observed in the experiment, in which the hybridization at the end is reflected in the density of the state in a way that you have a single peak, you hybridize, and you get two peaks. So this is...
Sorry, the hybridized state is only the lower energy of those two peaks.
Because the density of states give you the possible transitions, so you can see both. You can see the two possible transitions.
What are the two possible transitions?
So you can the excitations of the system. So you can see the ground state, but also the excited state. So you can see the bonding or the anti-bonding. You can see both states. So then you see a peak, okay? And when the barrier between the two dots, here you have the two dots, okay? And here you see the Kondo peak of each dot. They are now put in contact, okay, through this barrier here, and then you see this double peak, Okay? And this happens always that the occupation of each dot is odd, which means that the two dots, they are making their own Kondo effect. Okay? So these are the bonding and anti-bonding states. And now this physics was already explored, but now you can have also super exchange interaction between the spin of the two dots, which means that now you have each dot develop its own Kondo resonance. Okay? And now the localized spins, they can generate through this barrier. Okay? You can generate what I told at the beginning. They can generate an antiferromagnetic interaction between the two spins. Okay? So then you have a competition between two types of singlets. One singlet is the Kondo state, here or here, and the other singlet is the one that is formed by the two localized sites. And then this will give you some type of quantum phase transition. Okay? This is what I said. So you have the Kondo cloud, okay, and now they want to talk each other through this antiferromagnetic exchange spin-spin coupling. So if the exchange coupling is larger than Tk, you will see again two peaks in the density of states. And if the Kondo temperature is larger than J, then you only see Kondo effect. So this is what we study. So in one word, we study how you can see the transition from single peak to a double peak. And the double peak now reflects the formation of a singlet state by the two localized sites. Okay. So since I'm almost doing my time, I just wanted to tell you that when you have two quantum dots, they can talk each other because of the antiferromagnetic interaction between them. Okay, and you have on top of that Kondo physics. Okay, so when this J gains, you have double peak, and when Tk gains, you have just single peak. Okay. So this is the same. You can build a kind of Kondo, a kind of phase diagram where by moving the Kondo temperature, you can favor the Kondo phase or the antiferromagnetic phase. Okay, so here you have transport because the two Kondo states, they favor transport, and the antiferromagnetic phase, in that situation you don't have transport because the two spins of the two dots, they are locked into a singlet state. Now, with a spin polarized contact, I'm arriving to the end. Now we substitute the contact, the normal contact, by some spin polarized contacts in this way. Before of that, I wanted to mention that there are experiments on this type of systems where Kondo effect has been seen in the presence of ferromagnetic contacts, and the main signature of the ferromagnetic contact is that the Kondo peak is split. Okay, because of this. The explanation is the following. Okay. There are many other experiments in atomic contact. This was done in a Spanish group in Alicante, I think, by people from there. And even with superconductors, this was in a group in Regensburg. So now there are plenty of experiments dealing with ferromagnetics and Kondo effect. Even in a Japanese group, they even applied not a ferromagnetic contact, but they apply some spin bias voltage, for instance, and they also observe some splitting in the Kondo peak. This is the DIDB again. So what happens with ferromagnetic contacts is the following. When you have ferromagnetic contacts, we model in this way. We consider that we have different density of states for spins up, for instance, than for a spin down. And we can have two different situations. When the contacts are parallel or anti-parallel. This means the following. So, due to the different density of states for up and down electrons, the probability of tunneling between the reservoirs and the dot are spin dependent. So to transport one electron from here to here, they see different barriers depending on the spin orientation. Okay. This is the ingredient in the theoretical model. For the parallel case, we assume that the majority spins point in the same direction in the left and the right. Okay, and we can model the couplings, the tunneling rates using this type of parametrization, where P is just giving the degree of polarization. So the antiparallel case is just a situation where you reverse the majority and minority character from the left to the right. Okay. So this is antiparallel and the previous one was parallel. So what happens when you have this type of situation, when you have different tunneling rates depending on the spin in the parallel and in the antiparallel situation? What happens is that here I plot some result that we obtained previously in 2004, and this was a parallel work by other people. And what happened at the end is that due to the ferromagnetic contact, there is an induced magnetic field, which means that the level of the dot split. And this is because of the ferromagnetic contact. The up and down dot spin level is renormalized differently because you have different transparencies depending on the spin direction. So if you renormalize in a different manner up and down electron, at the end the normalization just gives you some splitting between the up and down dot level of the dot level. Okay, so then this means that if you have some ferromagnetic contact, then you have some exchange field, and this means that the Kondo effect is split, and here we plot the splitting versus the gate of the dot, because the splitting not only depends linearly on the polarization, but also depends on the occupation of the dot. And what is important is that in the symmetric case, when the dot level is half of the Coulomb interaction, this point here, this effective magnetic field due to the polarized contact just disappears. Okay. So now I'm almost finishing. Sorry for having too many things. So with two quantum dots, what happens is that now the Kondo temperature depends on the polarization, and you have two situations. One situation is what we call the particle-Hall symmetry point. In the particle-Hall symmetry point, the only thing that the ferromagnetic contact do is just to have different Kondo temperature. So Tk depends on P, independently if you are in the parallel or in the parallel situation. So Tk depends on P. So which means that you can vary P in a way to have a transition where Tk is smaller than J, the antiferromagnetic coupling between the two dots. Okay. So in the symmetric case, there is no exchange field, and then the transition from the antiferromagnetic phase to the Kondo phase is just done by tuning P. Okay, this is what the results shows, that by increasing P, okay, in this case, for instance, we see a single peak that at the end is just a double peak. Okay, and this is similar physics for the parallel to the anti-parallel case. Now, I'm finished with this. If you have exchange field due to the ferromagnetic contact, okay, you have two situations. The parallel one, which means that the exchange field for the dot 1 and the dot 2 point in the same direction. But for the anti-parallel case, they are anti-aligned. Okay? So now we have two magnetic fields in each quantum dot, and they are parallel or anti-parallel, depending on the ferromagnetic arrangement of the contacts. So this now can be compared with the antiferromagnetic interaction between the two dots. As I said, due to the barrier between the two dots, you have some antiferromagnetic interaction in this way. But you can look at this interaction in a midfield manner, where this part, for instance, is type of magnetic field for the spin 2, okay, like this. You can write this type of interaction as a magnetic field. In the way that you can compensate the exchange field of the contact by the antiferromagnetic coupling between the two dots, because you can look at this interaction like an effective magnetic field. But you can only compensate if you are in the parallel situation, because the exchange field of the two dots point in the same direction. So you can compensate by generating an exchange field in the other direction, okay, by this interaction. And how you can tune this? Since J is depending on T, you can vary the transparency of the barrier, and you can tune in a way to compensate the exchange field of the ferromagnetic contact. So by properly tuning the interdot tunneling amplitude, the exchange field generated by the polarization can be compensated only in the parallel case, because in the antiparallel case, both magnetic fields are just pointing as just anti-aligning. Okay, so the antiferromagnetic speed interaction cancels the effective field from the ferromagnetic contact, but only in the parallel case. And this is the previous to the last transparency. And here you see how by tuning, well, this is the density of state for up and down electron. The total density is the sum of both. So if you move the interdot tunneling, you are tuning the antiferromagnetic spin interaction between the two dots, and you can compensate this splitting. Okay, here the splitting maybe is not seen in a very good manner, but it's just a different position between the blue and the green core, give you the splitting due to the effective magnetic field. Okay, and you see how, for instance, in this situation, the two peaks are just one below the other, which means that there is no splitting. Okay? So as long as you increase the T value, you can tune to a point in which the magnetic field induced by the ferromagnetic contact is compensated by the antiferromagnetic spin interaction between the two dots. Okay, and I'm done here. So the conclusions are that in the double dot system attached to normal leads, you always have bonding and antibonding Kondo physics, and you can have also antiferromagnetic Kondo crossover in serial double dots, which means that you can go from the Kondo phase to antiferromagnetic spin singlet state between the two dots, the two spin of the dots. Okay? And when you attach ferromagnetic contacts for the particle hole symmetry case, you can make the Kondo effect weaker with the polarization, and away this point you have this magnetic field that is induced by the ferromagnetic contact, and in the parallel case you can restore the Kondo effect by tuning the interdot tunneling rate. So I think that I'm finished.
Thank you very much for staying, especially for staying in time. You know, so we started late.
Well, I think that.
No, we started almost at 10 after.
Yes.
So is there still any question?
In the experiment, how do they produce the spin polarization in the method?
In the experiments, they use some ferromagnetic contacts. I mean, they are ferromagnetic, like nickel, for instance. And using the hysteresis diagram, I think they can change the axis of the polarization. They can turn from parallel to anti-parallel.
You also create some kind of magnetic doping, and then when the electrons propagate through the magnetic doping, you get the polarization. But the exact effect
Semiconductor for
yeah.
I think that here they are ferromagnetic, yes, materials by itself.
Could you put again this transparency, this reference of 2002 with Lodia, on which we have a DIDB curve?
2002, yes. Yes, yeah, I know.
Here, the next one.
Yes.
What is the curve to the
Yes.
to the left?
This is the current.
This
This is the current. The current versus
to the not to the gate voltage, but to the
drain source. Yes, to the applied bias.
So this is completely different physics from what we have.
No, this is the same. If you take the derivative of this,
Yeah, but
you get this.
Yes, but this is the slope. But all the things you have told us were in the linear regime. The first.
Yes.
So
Well,
what
yes.
happens the second part? This negative resistance.
Well, I have shown, I think, linear and non-linear. I have shown this is the linear conductance and this is the DIDB. Yes.
But probably in the non-linear regime, this is not related to the density of the states.
The DIDB to the density of the states, people say that is related, but actually, if the voltage is a bit, yes, if you are really in the non-linear, then you have some effects that are not included in the transmission. I mean, people just take the transmission through the dot independent on the applied voltage. And then the current is the transmission and the difference of the Fermi function. You just take the transmission out.
Yeah,
but
in
this
the
is
curve
not.
you have shown this drop in the
Well,
intensity.
no,
of
but
this.
this is a problem of the approximation. This is a problem of the approximation. It's a slave boson approximation that when you make something to the system, then fails.
Okay, so it's not a new effect, but
No. And
breakdown
this,
of the-
and since you have to solve some nonlinear equations here, you can even have some spurious solution, and you can have even the stability, but this is related to the method. Okay. Yes, this should be something like that, with a smooth. Or yes, it's just this approximation just show you that you have a splitting. That's all. When you go from the Kondo to the antiferromagnetic phase.
One question more?
Okay. If you imagine an array of quantum dots who are enlightened in such a manner that it's always the respective anti-parallel configuration, then could you hypothetically imagine some kind of long-distance entanglement or something?
You have an array of quantum dot, and at the end you have some Kondo clouds.
There's some kind of bias on the one side, and then some kind of spin entanglement from one side of the array.
I think that there are some people that have studied this type of things. I mean, just the entanglement between the delocalized electrons in the Kondo cloud and the localized spin in the quantum dot. And for some arrays of quantum dot, I think that there are also some work on that. But I think that for two dots, the physics is very non-trivial. So for many dots, I guess that this is kind of mess. But this has been studied also by people on Kondo lattices, for instance, in which you have many of these sides, and they are connected to each other, and then you have around a method that each side is doing its own spin Kondo phase. But I think that this is a very non-trivial problem. Even with two is quite fast. Thank you.
No more questions? Well, before finishing, I would like to say that Rosa and myself will be organizing the seminar since February 22nd. I think it's our first seminar.
Yes.
So this is still, I'm only sharing because Ernesto is not here. We have already talked to the students and we have a number of changes like priority for students for questions and so on. This was not effective yet today.
But it was very
I'm
nice
glad that you constantly people ask, but soon will be more changes. But this is not our job. And something else only, I have counted 10 students that were here. You were 16 in our meeting the other day. I mean, principal assistance to the attendance to IFISC seminar is mandatory for students.
Maybe
I sent an email to the other 6.
they know.
Okay, so let's take a picture.
So that's the original
Sí.
Sí, ya me pido, lo puedo llevar.
Sí,